Ventilation is the intentional introduction of ambient air into a space to control indoor air quality and displacing indoor pollutant. The correct introduction of ambient air will help to achieve desired indoor comfort level. Natural ventilation is the process of supplying air to and removing air from an indoor space without using mechanical systems. The design of buildings that promote occupants' health and well-being requires clear understanding of the way that ventilation airflow interacts. This exercise is meant to study natural ventilation in an office building in Manchester City by exploring its ordinary status and suggest a strategy to enhance both natural ventilation and energy consumption in the building. The site is a 3,560 meter square plot stationed in a multi-use area within the city center. It's located near the intersection of Oxford Road and the Mancunian Way. The weather in Manchester tends to be moderate to cold. Temperatures ranges from 7 to 13 degrees Celsius in January, where the sun comes out for 8 hours only, and between 18 to 29 degrees Celsius in August. Temperatures exceeds 24 degrees Celsius for short periods of times during 4 months only. Most dominant wind comes from the west, averaging at 10 meters per second. The site is currently fenced but unoccupied. Following are some street-level imageries of the site. The building under assessment is a small open-plan 2 stories office building with one core in the center. For a more accurate results, the building codes were reviewed and the minimum U-value standards were applied in the 3D performance analysis software used for this exercise, the BUiD. U-values were applied for external walls, floors, roofs, and windows. And when analyzing the site, 2 structures of possible effect on the analysis were identified. The first is a complex of 3 15-story students' residence, and the second is a vehicle bridge. These structures can cast shadows and obstruct winds, hence were included. The computational fluid dynamics analysis was used in 2 main steps. The first is to identify the best orientation of the building in terms of energy use and heat gain. 4 positions were chosen for the analysis, as the positions should be implementable and valid on the site. 62 degrees from north. Suncast analysis is used to perform shading and solar insulation studies. External computational fluid dynamic analysis shows the effect on the building caused by the dominant wind, showing wind speed, direction, and overall pressure. 52 degrees from north. Suncast analysis. External wind analysis. .42 degrees from north. Suncast analysis. .32 degrees from north. Suncast analysis. In order to find a favorable orientation, number of values were extracted and compared. The main values of interest are total energy consumptions, total carbon emissions, and solar gains of the main spaces. When comparing energy side by side of the 4 scenarios, it's clear that N332 is the best to go with. It uses as much as half the energy of N152, proving the importance of properly orienting a building. Total carbon emissions also came to be less, as well as for total heat gain. For N332, all windows are oriented to the north away from direct sunlight. From the previous graphs, it's clear that the favorable orientation is the N332. For further clarification of wind on the building at the favorable orientation, it was simulated using flow design. All main winds, not just the dominant, hit the building at the facades that lacks any windows. It's important to visualize and understand the internal situation before moving forward. Internal CFD shows the behavior of air current in the main spaces. The ground floor shows slow air current moving from the sides to the middle at the floor level and the opposite at the ceiling level. The main spaces in the first floor exhibits faster current of almost similar patterns, and currents from the left sides are stronger here than the ones in the ground floor due to the window that doesn't exist there. The second step is to introduce a natural ventilation strategy to further enhance the situation. Wind catcher is the strategy of choice. A basic model was chosen from a UK-based company producing very sophisticated wind catchers. The analysis was undertaken for 5 scenarios in total. The scenarios are divided between 2 locations. Location 1 was chosen at the deepest place away from windows. That's for better air circulation and more even distribution of temperature and pressure. The first scenario at location 1 has 3 wind catchers with opening facing the dominant wind. The second scenario at location 1 has 3 wind catchers having opposite openings, where only one of the opening faces the dominant wind. As location 1 mainly favored the first floor, location 2 was chosen at the core in order to deliver more air to the ground floor, assuming the doors are kept open. Scenario 3 has 2 wind catchers having openings facing the dominant wind. Scenario 4 has 2 wind catchers with opening at the opposite ends, one of them at the dominant wind direction. Scenario 5 is quite unique, where it tries to dedicate one wind catcher entirely for air entering the core and the second for air exhaust. When comparing the results of the total energy with the base case, some savings can be found. The savings are not significant as the main load in buildings for such cities are the heating loads. When comparing the scenarios of the first locations, energy use is almost 95% of the base case. Where the scenarios utilizing the core and with wind catchers working as intakes and exhausts yielded the least energy at 93.9% of the base case. Internal air currents are now slightly faster, especially in the ground floor, while keeping the same patterns of the base case. Hence, the best scenario is number 4, resulting in 93.3% of energy use and 94.1% of carbon emissions. In order to further comprehend the results, a quick exercise was undertaken to review BREEAM. BREEAM is the sustainability assessment method used in the UK. It focuses on sustainable value across a range of categories, including energy, pollution, health and well-being. Providing proper ventilation for the building would grant 1 credit. In addition, for the reduction of energy use and carbon emission, the building can get up to 9 credits for energy performance and up to 4 credits for prediction of operational energy consumption using energy modeling. Given the process undertaken in this exercise, this building should get a minimum of 3 credits with the ability to reach up to 9 credits. Thank you for watching.